Let's look at a slightly more complicated example here. Let's consider the curve given by this beautiful looking equation. Again, I hope you see there's a lot of symmetry here. You could probably swap the x's and y's and get exactly the same thing back, which is shown by the fact that this is symmetric about the x and the y-axis. This is called the Lemniscate of Jacob, or Jakob, maybe, Bernoulli. This is the same Bernoulli family that you met in physics class, if you have seen them there, for Bernoulli's principle. Bernoulli's principle is named after Daniel Bernoulli, who came up with it. He is the nephew of Jacob Bernoulli, and we'll have the chance to see more about the Bernoulli family later this week. One interesting fact that I'll mention right now about Jacob Bernoulli is that he solved what is called the tautochrone problem. We have an applet for you to explore the tautochrone problem. They were very interested in finding, for the purpose of designing more accurate clocks, finding a curve where no matter where you placed a, let's say, frictionless ball, rolling ball, whether you placed it high up on the curve or low down on the curve, it would always take the same amount of time to get to the bottom. Meaning that if you placed it high up on the curve, it would start to go down really fast. And if you placed it low on the curve, it would start to descend more slowly. And no matter where you placed it on the curve, the ball would always get to the bottom in the exact same amount of time. And we have this really, I think, cool looking applet for you to play with. You can put the balls in different places and watch them slide down to the bottom in exactly the same amount of time. So Jacob Bernoulli was the one who used calculus to solve this. Christian Huygens had already solved it using a geometrical approach, but Bernoulli's approach in many ways is more satisfactory and more rigorous, using calculus instead of geometry. And yeah, so please take a look at that applet. Meanwhile, let's try to see if we can figure out what the derivative, the slope, of Bernoulli's Lemniscate is. Probably last time several of you out in the audience knew what the word folium meant, that it meant was Latin for leaf. What do you think Lemniscate is Latin for? Lemniscate is Latin for ribbon. This sort of looks like a ribbon, you can imagine twisting upon itself. Let's take the derivative and find the derivative of this equation. Again, this is a fourth degree equation, meaning that there is a way to solve for y in terms of x, as we said before. And if you know how to do it, please go ahead and do it. I don't know how to do it. We're just going to leave it the way it is and take the derivative this way. So nothing unusual is happening with 2x to the fourth. That just becomes 8x cubed when we take the derivative. Here, what rule are we going to have to use for 4x squared y squared? We're going to need the product rule. So the derivative of 4x squared is just 8x. And we multiply that by the y squared. Then we leave the 4x squared alone. And now we have to take the derivative of y squared. And this is where something unusual happens, as it did in the previous example. You can think about y squared. If we had been able to find some big, long formula for y, you have that whole formula there squared. So you have one function inside of another, which is a clue that you need to use the chain rule here. So we've got something squared. So the derivative of something squared is 2 times the something, and then times the derivative of the inside function, which you could call y prime if you wanted to sort of live dangerously and have y's and y primes all running around together in here. But I'm going to call it dy dx because that's easier to distinguish from just a y in this equation. And then we've got 2y to the fourth. That's also an example where we have one function inside of another, so that's a chain rule. The 4 comes down. We get 8y cubed. And then chain rule says we have to attach a dy dx at the end. We can move to the other side now. Nothing unusual happening with 25x squared. Derivative of that is 50x. And 25y squared becomes 50y. But don't forget to use the chain rule and get a dy dx there at the end. So now, just as in our first example, this has turned into an algebra problem. We're trying to solve for dy dx. We want to get them all on one side. We've already got 2 of them on this side, so I'm going to move the 50y over to that side and move these 2 terms over to the right side. So the 50y dy dx will come over here. I'm going to combine this all into one term. I'm going to call it 8x squared y dy dx plus the 8y cubed dy dx that we already had. I already had a 50x on this side. And then I'm going to subtract these 2 terms to the right side. now it should be pretty smooth sailing. We've got 3 dy dx's all on one side. We wish we only had one of them, so we can factor out a dy dx. And we'll have 50y plus 8x squared y plus 8y cubed. Nothing changes on the right side. And then the last step is just to divide. We're going to divide that 50y, this whole term, over to the right side. And just as it was in the first example, it's no surprise that we have both x's and y's involved in our formula for the slope of the tangent line, because just as it was in the first example, if you only know the x value, you probably don't know where you are on the curve. Right? If I went over to whatever this x value is here, there's 2 different slopes there. So we need to know the x value and the y value in order to be able to figure out what the slope of the curve is at a given point. All right. I hope you enjoyed implicit differentiation. We have a check your understanding for you. We have the applet for the tautochrone problem. Tautochrone, if I didn't mention it, tauto means same, chrone means time, so same time. That's the name of the problem that Bernoulli was famously solved, one of the problems that he famously solved. And we have an applet to let you explore this beautiful lemniscate, and we have a check your understanding on implicit differentiation.